Now that we have looked at the various configurations of RNNs that are typically used, they are widely used in tasks where you have variable number of inputs and outputs, as well as where you have these time-dependent data. However, these RNNs can be a bit unstable while you're training them. And in this video, we will look at why which is so. Let's get started.
Difficulties in training recurrent neural networks. As we discussed, RNNs have this repeated function composition as you apply the same mappings to your state over and over again. This does have an advantage in the sense that it creates more and more nonlinear versions of the inputs that are captured in the state. Here in this illustration, you see what happens if you apply the function mappings repeatedly. So you start with a line, as you see here, and if you apply the function mapping once, you get this sort of curve, and we see that this becomes more and more complex progressively. So this is really great. So long as the input is given in the hidden state and it is mapped over and over again, you get these more non-linear representations of your inputs and your state. However, this repeated function composition also creates a problem. Now, in order to illustrate, let's take a look at this recurrence relation in the form that it is shown here. So for the moment, let's not consider any inputs and outputs. So the hidden state gets mapped from one time step to another using a recurrent matrix W. And since W is the same matrix that's applied to the mappings, we can write it as applying the matrix W transpose times the hidden state from the previous time step. So if you remember, it is the same mapping that's applied over and over again. So if we decompose the weight matrix in terms of its eigenvalues and the eigenvectors, we can see that this raises the eigenvalues to the power. And now the eigenvalues that are below 1 will basically vanish over time. And imagine if you have something that is smaller than 1, and then you multiply it with something that's again smaller than 1, and so on. So it becomes lesser and lesser. Whereas now if you have something that is larger than 1, it will become larger and larger. So we can say that this component will explode in the case that it is larger than 1, and this component will vanish if it is less than 1. Now, if the input vector that you have aligned with the eigenvalues that are larger than 1, they will become larger and then explode. And the ones that align with the eigenvalues that are less than 1 will now vanish. So recurrent neural networks are more complex than this because we have inputs that are coming in which influence the state of one of the network. Now let's see an illustration of this. Here we have the network unrolled over the different time steps. And if we perform the backward pass, you have multiplications of the weights W and the derivatives, including the activation function. So if the absolute value of the product of these two, which is basically this, is larger than 1, then you get an exponential increase, which leads to oscillating weights. And you don't make much progress in your optimization. Now, if the absolute value is less than 1, you get an exponential decrease, which also leads to small gradients which vanish over time. So these two problems of vanishing and exploding gradients plague the optimization of recurrent neural networks. So what can we do about this? So one way to deal with this exploding gradient problem is to just clip the gradient. Note that we still take the direction of the gradient, but we just restrict its magnitude. So if we look at the plot of the error surface with respect to the weights and bias parameters, you always want to go to the region where there is low error. However, on the left, you see here we have no gradient clipping. So as the optimization basically progresses, you maybe will overshoot because your learning rate is not tuned properly. Whereas you would want to go to the ravine here as in this location. So this overshooting would then lead to a huge gradient at this location. And because you want to go to these low error region again, this would then lead you to a region here outside, which is maybe worse than what you were before. So now with gradient clipping, you restrict the step which you take to get when you get a large gradient. So you will still go up, but you only take these really small steps and not this really large step as you see on the left. Then it's easier to go back down because you take only smaller steps. So this way of elevating the exploding gradient problem is called gradient clipping. If you have vanishing gradients, you can use long short-term memory networks, and we will discuss these long short-term memory networks or LSTMs in the following videos. All right, so this brings us to the end of this video. I have two questions for you. What are the two most common problems that can affect the training of recurrent neural networks? And what are some solutions to alleviate this problem? Now I encourage you to pause this video at this point and try to answer these two questions. Thank you, and I will see you in the next video.